Here is a frozen yogurt machine. You fill a cup with yogurt and then get it weighed. It costs 59 cents per ounce. Since the cup weighs about a half an ounce, you end up paying 29 cents for just the cup, plus the amount for the yogurt. Next to the cup is a scale that shows how much the yogurt will cost. It already shows a cost of 29 cents for the cup. I'll play an animation showing frozen yogurt being dispensed into the cup. As you watch the animation, think about the relationship between the weight of frozen yogurt in the cup and the total cost. In particular, you'll need to determine whether the rate of change of total cost with respect to weight of yogurt is constant, increasing, decreasing, both increasing and decreasing, or something else. I'll start the animation now. The answer is that the total cost changes at a constant rate with respect to the weight of frozen yogurt that is added to the cup. Let's think about why this is. First, I'll represent the total cost. The green line represents the cost of the cup itself. And I'll represent the change in the cost using a blue line. Next, I'll represent the weight of the frozen yogurt that gets added to the cup using a red arrow. Let's rewind this to the start of the dispensing. Now I'll show this again. As the animation plays, think about how the weight of the yogurt, the length of the red arrow, and the additional cost, the length of the blue bar, are changing with respect to each other. Next, I'll add black bars to indicate the change in weight. So on the bottom, the distance between the bars is showing the amount of change in weight in ounces. We can copy this length onto the cost bar. Now, if we think about the amount of change in cost in dollars, we can see that delta cost is roughly 0.59 times as large as delta weight. Let's rewind the animation. Let's play the animation again, this time incorporating the black bars to show the amount of change in weight. Now, it's not the case that the total cost was always a fixed multiple of the change in weight. This is because we had to pay for the cup before we started adding any yogurt. However, what you might have noticed is that no matter how large delta ounces was, delta cost, measured in dollars, was always about 0.59 times as large as delta weight, measured in ounces. This is what it means to have a constant rate of change. In this scenario, total cost and added weight vary at a constant rate of 0.59 with respect to each other if the amount of change in cost is always 0.59 times as large as the amount of change in weight. We can also think about how this would work if, instead of treating the added weight of frozen yogurt as a single large part, we split our weight into two equal-sized parts. To make things a little easier to see, let's rotate the height bar. It's still the case that, for each of the two sections of added weight, the amount of change of cost is about 0.59 times as large as the amount of change in weight. What if we'd used a different number of sections? Let's split the added weight into 5 sections. It's still the case that, for each of the 5 sections of change in weight, the amount of change of cost is about 0.59 times as large as the amount of change in weight. This was true whether we split the added weight into 2 equal sections or 5 equal sections, and would be true for any way of splitting it into equal sections. So a consequence of our definition of constant rate of change is, for every fixed amount of change in weight, the amount of change in cost is constant. So now we have 2 ways to think about what it means for the height of the water to change at a constant rate with respect to the volume of added water. And if we think about the examples we've seen, we can summarize the notion of constant rate of change in the following way. Two quantities vary at a constant rate with respect to each other if changes in their measures are proportional.